Okay, our next presentation is by Keith Bryant. He is a technology consultant, and his presentation, Are We Ready for i4.0? Keith, I will leave it to you.
Thanks, David. Good afternoon, ladies and gentlemen. If I could have put together the presentations that you've seen already to lead into my presentation, I could probably have not done a much better job. We've heard about the issues with printing. We've heard about, and I thought it was a very honest comment from Mark that, yeah, Industry 4.0, we want all the machines to talk to each other, but once you've got the reflow machine set up, please don't keep retweaking it because it'll create a complete nightmare. I'm a mechanical and production engineer, and I agree with this 100%. You know, the linking of machines and the talking to each other, it's a great concept, it's a great theory. My question is really, are we there yet? And probably this will follow on from some of the stuff you've heard this morning, and also from our last presenter about where the intelligence is within the production line. One comment that I will make is I have pictures of machines in my presentation. Please don't think of them as the good ones or the bad ones. They're just generic images to demonstrate what I want to do. And you know, what I like about this slide is a saying I learned a long time ago as an apprentice. If you ask 6 experts for an opinion, you'll always get 6 different answers. And it's as true today as it was then. But let's just assume that somewhere between 50 and maybe even more than 70% of the faults that we see at the end of the line, in other words, they're faults, they're things we have to fix. They're not defects. A defect is something that's not perfect. A fault is something that has to be fixed. So let's pick an average and say 65% of them come from the printer. And again, this is just a generic image. The issue that I have with our production lines is some machines are really intelligent. Some machines, like the printers, are a bit dumb. But this guy's responsible for probably 65% of our faults. So let's look at a single fault that's found by a good 3D SPI machine sat in the production line immediately after the printer. And it says, okay, insufficient paste. I won't go through all of the lists. If we have any process engineers here, they can probably add 5 or 6 things to that list. But the important thing to get over is there may be a lot of different reasons for that one fault, okay? And if we look at the basics of i4.0, it's taking automatic feedback to improve production. Feedback in our world at the moment generally is based on algorithms. An algorithm, by definition, has a single result. So what does the printer give the SPI to make this decision? The gentleman from Young earlier said, okay, 3 parameters, squeegee speed, squeegee pressure, and snap off. Well, some printers you can change your snap off speed, some printers you're stuck with it. I spent 10 years in a business with solder paste, and we always told customers, just use the snap-off speed that we recommend for the paste. Basically, set it up, don't mess with it. The same theory as your reflow oven, yeah? If it's there, leave it alone. So really, as a general rule, you probably don't want to be tweaking it. So let's say the default algorithm for insufficient paste is not enough squeegee pressure, okay? It might be one of the others. So increasing the squeegee pressure as a result of what you've seen from 3D SPI may make the problem better. It may actually make the problem worse. And then if it makes it worse, it'll probably go back to doing one other thing that may also not be the one thing that fixes the problem. And by then you've probably contaminated the underside of your stencil and you've got a whole load of other problems anyway. The issue that we have is the data that we get from the printer. It's very, very minimal. And as the gentleman said previously about measurement, data is the most important feedback that we need. It's a common saying, data is power. You need the data to make the good decisions. The more data you have, the more chance there is of making the right decision. And if you don't have it, you're guessing. And if you're guessing, you're living in a world that, as production engineers and process engineers, we don't like to live in. So the solution, very simply, is we have to make this guy smarter than he is. We make him smarter, he produces more data. He produces more data, the SPI can produce a more accurate result, and we're more likely to have a situation where the feedback fixes the problem. So, simple things that we can do well, we can't do them, but as simple things that the people that build the printers can do. Weigh the stencil after you printed. If you're worrying about insufficient paste and you know the stencil is the right weight that it should be for the stencil plus paste, you can be pretty sure that that's not the problem. So you set a minimum and a maximum limit, and that's going to tell you too little paste or too much paste. Both of them can cause different problems, but I'm not going to speculate as to which one's worse than the other one, because again, if you ask 6 engineers, you'll probably get 6 different answers. Something else that in my days playing with solder paste that we really suffered from was flux and moisture. Too much flux and the paste slumps. Also, it doesn't roll well. Too little paste and it becomes sticky. It sticks in the apertures. It sticks to the squeegee. It sticks all the places it's not supposed to be. A lot of flux chemistries that are out there are hygroscopic. That means they pull water in from the environment. So over time, they become more wet than they were when you started using them. And the paste will perform differently depending on the amount of moisture that's with it. Another issue, coplanarity and board support. Coplanarity obviously gives you inconsistent printing because the two things aren't parallel to each other. It's basic. And again, poor bad support, poor gasketing, missing paste, too much paste, bridging. I even missed underside stencil contamination off this one because there are so many things that you can do and so many things that you have a problem with. Some enlightened companies and the more, let's say, the more expensive printers, they're in a temperature and humidity controlled cabinet. So basically you have your own little mini environment that your solder paste is running in. This helps because the consistent temperature of the paste means that you have consistent rheology, and the humidity control means that you don't get too much moisture sucked into your paste. I'm actually a fan of the fully enclosed print heads, the Rio Pump, the ProFlow, and now there are some third-party ones out there as well. The reason why I like them is they keep the solder paste completely contained, and they keep a constant pressure on the solder paste as it's going over the stencil. So these are, for me, a step in the right direction because they take away some of the variables. And the more variables you can get rid of, the more consistency you have. Yeah? But we've still got a long way to go, and please remember, I'm just looking at and talking about the printer. So, if we wanted to, what could we sense? As the gentleman said before, sensors are the important things. Sensors give us the feedback, sensors give us the data, and bottom line, sensors tell us what the hell's going on with our production line. If you don't have enough sensors, you don't have enough data. You don't have enough data, you can't make informed decisions. You can't make informed decisions, you can't get things right because we're living in that world of guessing. Yeah? So, very simple, if the printer's dumb, your production line's dumb. If you can make your printer smart, you're a step towards smart factory. So we need good algorithms, we need a good management information system to control all of this data when we've got it. Possibly at some time we also need the help of AI to make some of the decisions, but we definitely need to start with the basics. And like all the side, when I've just talked about the bad news until now, the good news and the good side of this is that printing generally is always the fastest part of the SMT line. That means that there's time to do stuff, yeah? If the printer was the bottleneck, you don't want to slow down the printer because you'll slow down your line. Because printers are very, very rarely a bottleneck in even the really fast consumer production lines, then there's chance to do something. And it's not really hard to get some of the feedback that I'm talking about. We already know maybe cabin environment, squeegee pressure, squeegee speed, stencil cleaning frequency. We've talked about snap-off, so I'll leave that one there. Volatiles evaporate easy from the paste. Yeah? We all know this. Moisture gets sucked in instead of the volatiles, so you're replacing the active components with an inactive component, and they're both wet. Yeah? Doesn't matter, you have too much of one, not enough of the other, you're going to get bad prints. Now, there's a lot of sensors out there that people use predominantly in their pot plants. They measure moisture and they measure pH. You simply basically push them into the soil and you get a reading, yeah? Now, the pH of paste changes as the volatiles leave, yeah? So you can probe the paste every 10 cycles with a simple little $2 probe, and it's going to tell you moisture, and it's going to tell you pH, which is going to tell you, is your paste within the acceptable parameters or not. So you have a $2 sensor every 10 prints, which is going to give you good, accurate, dynamic feedback. We talked about paste volume coplanarity. Put a piezo load cell on each corner of the stencil frame, and you're going to get stencil paste weight, because you'll get a total weight less the weight of the stencil equals the weight of the paste. You have a maximum and a minimum set. Very simple. You get stencil pressure real-time feedback while it's actually printing. This is going to tell you if the stencil's damaged, the squeegee's damaged, something's come loose in the machine, all of these things. It's going to tell you about stencil coplanarity, and it's going to tell you if there's a problem with your board support, because the pressure will vary as the stencil drops. It'll also tell you whether the stencil frame is worn, whether the stencil's warm. A change in tension will give you stencil damage. Warped frames give bad results. All of these things are real problems that any process engineers in the audience will be nodding their head, because we all live with these things. Yeah? Put a scanning camera underneath the stencil. Just get it to check a few of the key areas against let's say, a golden image. Very simple to do. And you clean the stencil when you need to clean it. You don't set up to clean the stencil every 10 prints, every 6 prints, every whatever. You set up to clean the stencil when you need to clean the stencil. So not only does this save you time, it saves you materials, it saves you a whole load of stuff, and it ensures that you clean the stencil when it needs cleaning, not every so many sections. So we've looked at all the bad stuff. Part of the production line already has a huge number of sensors on it. And it's inspection. Doesn't matter whether it's SPI, 2D AOI, or even better, 3D AOI, or we also look at AXI. This is where all the data is currently being found. Yeah? These are the machines that would normally be feeding back to the, let's say, the production machines on the production line about the things that are wrong. So, the problem we've got is getting the machines to work together and basically making them more intelligent than they are currently. Because whether it's AXI or AOI, they all have issues, capability problems, and limitations. Yeah? some good pictures, first of all, for anyone who's not sure what head-on pillow is. Yeah. And if you look at it in a cross-section, you're looking here, and this is an inverted image. So white is black, black is white, and what you're seeing here are actually voids within the system. But obviously, this isn't created from an inline system, because an inline system generally works in a different way. It has to find head and pillow fairly quickly, because these machines are sometimes the limiter in the production line. So you don't want the machine spending longer than it absolutely has to doing its inspection, because if it's the limit on the line, then you slow this machine down, you slow down the line, you slow down the line, you slow down your production. Now, an inline system works fairly simply. It takes a series of slices across the board. We have it taking 5 slices here. Now, depending on the result of those slices, it makes assumptions. Anybody who lives in the real world and uses AXI is aware of 2 words that bring fear into every quality manager's heart: false calls, and the one that really, really scares them is escapes. A false call is a good board that possibly gets flagged up as a bad board, but an escape is a bad board that gets out. And that's the real killer, and obviously people set up their machines to minimize the amount of escapes, which increases the level of false calls, because it's a balance, yeah? So if you're gonna swing this way, yeah, you're gonna stop a lot of boards that are good, and if you swing that way, you're gonna let out some boards that are bad. So generally, everybody sets their systems up to do this, yeah? Based on the measurements, they make an assumption that it's an open circuit. So they say, okay, the ball is small, the ball is round, therefore the ball has not reflowed. That's what they have to do because they're taking 5 measurements, okay? It's a big leap, especially now we live in the world of lead-free, because the balls and lead-free don't collapse as much as the tin lead balls used to anyway. So we're in a situation of, yeah, we're making an assumption. We're going to assume if the ball is smaller than this and the ball is rounder than that, it's an open circuit, yeah? And we'll set those limits to make sure nothing escapes. So just to give you an idea how the system looks, this is indicating a head-on pillow. You can see this ball. I can see how it looks just a little bit different to its neighbors. It's not hugely different, but it's just that little bit different as we go through the pictures. That's the difference when you're looking at let's say a system without perfect magnification and without the time to really inspect what's going on. Now, if you look at this image, I don't need the printer because I've put nice red arrows on this for anybody who couldn't work it out. Anybody not see the difference between the ball on the left with the red arrow and its brothers and sisters around it? No? Everybody see the difference? Okay, then you're all offline X-ray inspectors now, because that's basically all you need to do. It's the difference between an offline system where you have time, you have a whole load of other things, and an inline system which is running, trying to keep up with the speed of the production line. I threw this one in just to end the note. That's actually probably, unless it was a really high reliability system, that is just a crack on the outside of the ball. The ball is about 100 microns, so that crack is pretty small. It's not a complete through crack, it's only a crack on the outside, but it just demonstrates the capability of the new machines. Okay, now we're going to talk about 3D AOI. I've seen a lot of the systems. They're really good now compared to what they were in the early days, and compared to 2D, they have a huge number of advantages. The simple disadvantage with an AOI machine is if we can't see it with our eyes, the AOI machine can't see it. So if we talk about bottom-terminated devices, BTCs, bottom-terminated components, as people like to call them over here, BGAs, QFNs, flip chips, chip-on-boards, all of these things, 3D AOI cannot show you the joints. And again, this is a nice picture. It illustrates all the nasty things that can be happening to a system where the BGA, well, package on package in this case, is warped, and the board has also warped. Yeah? You've got everything from bridges to opens on the same component. All right, this is exaggerating a point to make a point. But obviously, all you can measure with the 3D AOI is the Z height. Yeah? If you've got a machine with Moray or laser or something, you can get very accurate difference between the board at the edge of the component and the edge of the component itself. And then you have to set a limit to what's good and what's bad. And that limit is based on history, it's based on a guess, it's based on work that you've done or whatever. But it's not a guarantee of a pass or a fail, because you don't know whether there's a joint or not, because with the system you can't see it. And again, this is just a generic. These images aren't here to sell a particular management information system or a control system. They're just here to demonstrate. And again, I've put a circle around the area which is in green. So that falls within the limits of the Z height. And you can see the other three corners are red. So the coplanarity of this component is out. So we need a way of finding out. X-ray is the greatest thing for looking underneath stuff without needing to destroy it. So here's the X-ray picture of what's going on under that component. Yep, it's a chip that escaped from the chip shooter. And invariably, they end up stuck to solder paste, and they end up stuck to solder paste, which you then put down components onto. It's called the law of Murphy for anybody who's not a process engineer, because every process engineer is well aware of the law of Murphy. Yeah? So effectively, this component is not flat because it's lifted, and as you can see, the balls and the pads don't line up very well. So yeah, it's going to be a nightmare. But the AOI system will just tell you that it's warped, or a coplanarity problem is wrong. So by putting the two systems together, you can actually come up with something that takes data from the sensors, makes use of it, and actually makes an informed decision about is that board good or bad. We all live in a world of statistical process control. We live in a world of needing to improve yields, improve production, improve first-time pass rates. If you don't know the reason for the failure, you don't know the root cause. If you don't know the root cause, you can't fix it. And if you can't fix it, you can't improve what you're doing. So what we're doing here is we're using an at-line X-ray system to be the verification machine for the unknowns which are happening in the production line. And this can be AXI, it can be 3D AOI. All you need is to link the machines together so that you can shift the data from one machine to another machine, and then you need to send it ideally to a management information system so the system can see what's going on with the production line. The aim being to keep everything happening within the process window, so you might create the occasional defect, but you don't create rejects, and you don't create scrap, and you don't create rework. Okay, this is a picture of the systems themselves. As I said, please ignore the machines, but effectively, here's your link, and obviously when you've got the data, you can output it in .csv, you can output it as XML, you can send it out as PDFs, you can save the images, you can store, if you're working in an aerospace and military environment, you can store all of this data on your server or in the cloud. It's all stored by part number, so you get all of the information that you need, And if you have a good management information system, you can have a feedback system like this, which shows you, and they're kind of in reverse order, but here's your SPC, here's your component, and here's your X-ray image. All of those are basically zoomable, and you have here image related to that component, and here you have image related, data related to the board, and as I said, you can save all of the images. So now you're in a situation where inspection and verification time is reduced because the only other way of dealing with the false calls is either throw them away, in-circuit test, function test, all the expensive end-of-line things that you have to do, and then you have to accept that possibly a percentage of those are going to be thrown away anyhow. 3D AOI is now a really meaningful tool because you don't have this issue of, okay, it's warped, but if it's a bottom-terminated component, are the joints good or bad? So there's a benefit. You still need a technician. We're not in this world of lights out factory. You still need somebody to look at that dashboard, to look at that management information system and make a decision. But now they have all the data that they need for intelligent feedback and improving the process. So let's say you've checked 30 boards that are all warped, let's say 40 microns, pull a number out of the air. And all of those boards have good joints underneath them. Now you can change the inspection limit of your 3D AOI machine a little bit wider because you know at that level they're all good. Yeah? So you're in a situation where you're continually improving your process. And this happens, I won't say minute by minute, but at least hour by hour, continuously through the time that you're producing. And you're all saying now, okay, Keith, it sounds wonderful, but what happens in the real world? So we convinced a couple of customers to go with this. And the first thing that we did was monitor what was happening on their production lines already. And this is always a difficult thing to get customers to do because you're measuring how much they get wrong. But these guys were actually up for the whole thing very strongly and were very prepared to look at the results and look at the differences. And I have to say, you know, they were a large multinational company, and I applaud them for having the vision. So generally, the time taken previously for about 10% of their production was 30 minutes a board. Okay, they were big boards. They weren't easy, simple little consumer boards, but even so, that's a lot of time. By using the, let's call it the closed loop, the pro loop, the smart loop, whatever name you would like to use, that verification time came down to 4.6 seconds per unit. So that's a pretty substantial saving in anybody's book, and that wasn't a cheated number. That included loading the board, pulling up the data, inspecting the board, taking it out, putting it in the good or the no good pile, and all the other stuff that needed doing. So if we look at numbers, and I admit, every time you do this, you're playing with numbers. I'm not a statistician, so I don't particularly love the ultimate use of statistics. But if you say that this system was 6.5 times more effective, 85% of the time and the cost of the rework was saved. Okay? We now assume that the operator who was using the X-ray machine got 5% wrong. Anybody who's ever driven an X-ray machine knows this is a crazy number. That number is going to be well less than 1%. But let's put 5% in there because it still proves to make a point. So if we make the assumption that all of the false calls were false calls, then your first time pass yield has gone up from 90% before using the system to 99.5, and that assumes 1 in 20 boards that the inspector looks at, they get wrong. So in itself, that is a it's a huge saving. It makes AXI, 3D AOI, a really strong process. It gets rid of false failure calls almost completely, because obviously there are other reasons for these, but anything which is related to BGA balls, opens, shorts underneath components, things that you can't see, basically you can fix with this system. And all the people who've seen it and other customers now have it implemented are very happy. At-line X-ray manufacturers are working with a lot of the AOI companies. I know Coy Young is partnering with at least one at-line X-ray company to develop this technology so that they are moving at least partway towards 4.0. My belief, we're not fully there yet. We're moving in the right direction. We need more intelligent printers. We need more data. We need more information so the machines can make more, let's say, more accurate and better judgments on the production line. But there are claims out there that yield is going to be 100%. We don't need people. We can switch the lights off in the factory. All of these things. We're not there yet, but we're moving in the right direction, and the more intelligent machines on the production line are leading the way to the others. But we need to get upgrades on the printers that will give us more data, more information, and then maybe we can start looking at the feedback from the SPI machine that addresses all of the potentials, because the SPI machine or the management information system connected to the SPI machine has more data. And at the moment as an engineer, I'm really glad that the best combination to control everything is a combination of our brain and the algorithms in the brain of the machine. So with that, ladies and gentlemen, I'm 1 minute over where I should be. So I will say thank you very much for listening, and I'll take any questions that you may have. No? Okay, that means I was either very bad or very good, so I'm going to assume I was very good, and thank you all for being a good audience.